because you're going to hear plenty about it, but this acronym, FRB 121102, it's a fast radio burst that occurred on November 2nd, 2012. That was when it was discovered, and unlike all the other ones, it repeats. And so it's been the subject of intense study, and today we're going to hear several results related to that. And we're going to hear from a number of speakers from both sides of the pond. We're going to start with Betsey Adams from, actually I'm not going to say their affiliations because they're on the signs and I'm not sure they're 100% correct, so I'll just introduce them. The problem is that, anyway, so Betsey Adams is going to begin. She's going to talk about how the location of this fast radio burst was pinpointed in its host galaxy. Then Andrew Seymour is going to speak about strange spectrotemporal features in this object's bursts. He'll be followed by Vishal Gajjar, who will speak on high-frequency observations of the source from Breakthrough Listen, which is the project that you've heard about that's listening for extraterrestrial intelligence, or signals at least. And then the next speaker will be Daniele Michilli. He's the one whose paper, he's the first author on the paper that's coming out in Nature today. I think everybody else is probably a co-author of that paper, or at least an author on one of the Apt J Letters papers that's also coming out. And then finally, and he's going to be talking about the extreme Magneto-Ionic environment. Okay, say that fast. And then finally, Jason Hessels, who was on the panel a year ago, is going to wrap it up and sort of help us take stock of what we know and what we don't yet know and what we're going to do next. So with that, I'm going to turn it over to Betsey. And we'll go. It should come up in just a second, right?
Yes, so to start this off, of course, you can see again the names and the contact information for all of us who are presenting here today. So in addition, there are a lot of other team members at this meeting, most of whom are in the audience. And so I believe the press will get a copy of this so that you also have the names and contact information for all of us. Yes, and so then I'm Betsey Adams. I'm a staff astronomer at ASTRON with an appointment also at the Kapteyn Astronomical Institute. And so I'm going to start with some background on this fast radio burst, 121102, and then talk about its connection, its location, and its host galaxy. And the takeaway message there is that it's located in a site of intense star formation, so we think the progenitor of this could have some connection to massive star formation or death. So before we start talking about this one special fast radio burst in detail, we should remind ourselves what a fast radio burst is. So they're millisecond bursts of radio waves, and they're typically one-off events. And what you see here on the right is the example, the prototype, the very first fast radio burst identified. And on your vertical axis, you have frequency, and on your horizontal axis, you have time. And that dark black line that sweeps through is the detection of the fast radio burst. And so what you see there is sort of a very intrinsic property of these bursts, which is that their signal is dispersed, that the high frequencies arrive sooner and the low frequencies arrive later. And we understand this is because of propagation effects as it travels through media. But what was surprising about fast radio bursts is that their dispersion is so large, their delay between the high frequency and low frequency is so long, that it implies they're traveling through more material than is in our own galaxy. So what that implies is these things are at cosmological distances, they're very far away in the universe, and we're seeing the effects of travel through the material between galaxies also. So their origin is unknown, but we know it must be really interesting and exciting because between the short duration and the fact that they come from so far away, they must be intrinsically very bright. So it's some sort of extreme physics that causes this emission, and so the goal is to understand that. What is the process that does this? And so as Rick already said, this source we'll be talking about today, this fast radio burst that was first detected in 2012, is very special because in 2016, we were able to announce that this is the first source that's been seen to have multiple bursts. And so here again on the right, we see a few of these bursts from that detection paper where we have frequency on the vertical axis and time on the horizontal axis. And now what we've done is we've removed this leg that we know about because we know that, so we take it out to look at the burst itself. And so this is exciting because first it immediately ruled out for this fast radio burst any sort of model that was cataclysmic or had an explosion, because you can't explode your source to have this emission and then explode it again. That's sort of a one-off thing. But more importantly, this also allows follow-up studies. Because this source keeps repeating and bursting again and again, we can continue to monitor it to understand it. And so that's exactly what the team has been doing. So as Rick said, last year at this very meeting, we had a press conference to announce that we had done this in order to localize this source. So we'd gone from looking at it with Arecibo, and you can see on the far right sort of the large Arecibo error circles in that figure, to pinpointing its location very precisely by using the VLA and then the EVN, and finding that in addition to this bursting source, there's a persistent radio source. And then we were also able to zoom in and look at optical data to identify the host galaxy of this source. And so now that we have the precise location, that allows even more follow-up to happen, because now you can point any telescope at this source and know that you're pointing at the source. So it doesn't matter what sort of field of view you have on your instrument, but you know you're looking in the right spot to detect it. And so what I want to talk a little bit about, because that's my expertise, is the host galaxy of this source. So we originally had Gemini data, and that allowed us to identify the host as a star-forming dwarf galaxy, so a galaxy much less massive than our own Milky Way, 3 billion light years away. And it's actually something that's similar to hosts of other transients we know about, like superluminous supernova or short gamma-ray bursts, which is very interesting. But in order to understand more about the host galaxy and what that might tell us about progenitors for the fast radio burst, we wanted to zoom into higher resolution. So we went from the Gemini images to using the Hubble Space Telescope to get higher resolution. And so here you can see that as we go to a Space Telescope, we gain resolution. So just again to see that we go from sort of a blur to distinct components of this galaxy. And so what we're actually able to do is say that all of that star formation that we'd seen in a spectrum from the Gemini telescope, we could now use the image to locate it in a single spot and say that spot is actually right where the fast radio burst and persistent radio source are located. And so this implies that there could maybe be some sort of connection to massive star formation or death, that there is probably not happenstance that that's where the fast radio burst is located, is in this site of star formation. And so now here we are in 2018 with a new press conference for you. And so what you're going to hear about next is how we're now using the bursts themselves to probe the local environment of this source. So to understand the immediate vicinity of what's happening here. So Andrew is going to start by telling you about surprising burst structure in time and frequency. And then Vishal will talk about how we've seen the burst at higher radio frequency. And Daniele will then give the main result that is in the Nature paper about how we've used the properties of the burst to know that there is a large magnetic field right near the source. And Jason is going to wrap up and give some possible models of a neutron star in different extreme environments. And so with that, I will hand it off to Andrew.
Hello, I'm Andrew Seymour from USRA that works at Arecibo. Today I'll be talking about these new features that we have seen within the bursts themselves, and we're uncertain whether these features are coming from the emission process or whether it's interacting from the local environment. So as you can imagine, with each one of these bursts, we want to learn as much as possible. So we've observed in the optical X-ray gamma ray, but the only thing that we have been able to record are these radio bursts. We had no detections. So therefore, we have to explore the radio burst more in depth and try to get as much information out as possible. As Betsey said, you can see on the left, these bursts come into the telescope higher frequencies first and lower frequencies later. This is an effect of actually due to its propagation to us as it travels, and we can correct for that as you see on the right. And FRBs appear to emit fully across our frequency band and nearly all at once, is what we thought. So if you look at one of our bursts at low resolution, it will look like that. And we have corrected for that larger sweep. But as we march to higher resolution, we can start to see smaller features that appear within this burst. And then if we didn't see those, we probably would have overcorrected, and we can refine that correction a little bit. Yet we're still having a pattern of from high to low frequencies, but it's different than what you saw in the last slide. To drive this point home of this, we've converted this burst to sound. So instead of a radio burst, you're going to hear a sound burst. Let me play it once for you. And this is 500 times longer than what it would be when it came in, when it was produced. Now, let me describe what's happening. You're starting to hear those high frequencies come in, and as those pauses are in there, those are the features that are coming out as well. Not all these features can be seen in both of those color maps, so we have printed out 3D models of these FRBs. And in the slides, there was a web address. And this burst right here on the podium in front of me has a lot of these smaller features there as well. So it's unclear whether these features are caused by it being emitted from the mechanism or whether it's interacting with the local environment, this downward slope. And it's also unclear whether if we were to crank the resolution up on other FRBs, we would see the same type of situation. So with that, I'm going to pass it on to Vishal.
Thanks, Andrew. So my name is Vishal. I'm a postdoc at UC Berkeley, and I work with Breakthrough Listen Lab. So as some of you might already know, Breakthrough Listen is actually one of the most comprehensive search for extraterrestrial intelligence. And we are basically currently operating at this Green Bank telescope that is shown here. We have a very powerful backend because if you want to do a detailed search for intelligent life, you need to have a very powerful backend. So that's what we have. We have a 32-node computing cluster which can actually analyze large amount of data simultaneously. So if I could just give you a little bit of feel for the amount of data that we collect per second. So we typically have 1 gigabytes per second input into one of the compute nodes, and we have 32 of them. So we are simultaneously sort of recording from all of these 32 compute nodes. So over an average, if you just record an hour-long data, you typically record something around 18,000 DVDs. That's quite a lot of data that we have. So that kind of gives you a rough idea about the amount of data that we have and then the amount of data that we need to handle. So this kind of gives us a little bit of an edge to kind of explore and push the limit of our backend to go and explore some of these FRBs and extreme pulsar phenomena. So that's what we did. We thought that why don't we observe these FRBs at the high frequency, because we had the flexibility of covering a large bandwidth. So that's what we did. We observed this repeating FRB at the highest frequency, starting from 4 to 8 gigahertz, and we got really lucky. So we observed it for 5 hours. So on the top figure, what I'm showing you here is the length of our entire Breakthrough Listen observation. So over the 5-hour stretch of the observation, we detected 18 of the bursts in just first 30 minutes of itself. But the rest of the observation, we didn't detect anything. So this is kind of telling us a little bit about the activity of the source itself, that it kind of becomes active and produces large number of bursts in a very short time. What I'm showing you here in the bottom plot is actually a zoom-in version of the first 30 minutes, and you can see the individual bursts there as well. So the reason why we detected so many bursts is quite clear if I show you the next slide. So what I'm showing you here, so each image is actually an image of individual bursts. On the top, you are seeing the burst profile, which is after the de-dispersion, what Andrew talked about. And the bottom, you are still seeing the dispersed pulses. So each image is actually an individual pulse. What you will notice here is that some of the pulses are more stronger. So the frequency starts from higher to low. So some of the bursts you could see are more stronger at the higher frequency, and some of them are more stronger at the lower frequency. Now imagine a case where you have a backend which only covers half of the band, then you will only be able to detect half of the pulses. So that was the reason why we were able to detect so many of the pulses in such a short time interval. Along with that, when we looked at in detail to some of these bursts, we also found, similar to lower frequency, that these burst structures that we have seen are also consistent at higher frequencies as well. So we are sort of releasing all the data, and if you are interested in sort of playing with it, there you can all download it from the website over there. So the other advantage of going to a higher frequency is that you are also able to see the detailed structures in the pulse itself. So these observations are not from Breakthrough Listen, but from the Arecibo telescope. So Arecibo has made some improvement in its hardware, and that's why they were able to push the frequency that they could observe to much higher frequencies. So now they could go as high as up to 5 gigahertz. So when they did the observation at 5 gigahertz, so what I'm showing you here is that if you look at the red curve, so that's the one of the burst. Now the width of the burst is only 30 microseconds. That's really tiny. And what it's telling us that if there is a burst which is size of 30 microseconds, the emission region itself has to be smaller than 10 kilometers. Now, 10 kilometers might seem big for you, but imagine this source is actually 3 billion light years away from us, and we are pinning down the emission to only 10 kilometers in size. That's kind of spectacular. And all this is possible because we are able to go to higher frequencies. So once we know that emission region is only 10 kilometers, we can pinpoint that what sort of sources can give rise to these emissions. And then there are not many sources which comes to mind. Neutron star is one of the most likely case, which Jason will talk more in detail. But one of the biggest advantage of going to higher frequency is to explore the magnetic field of the source. And that's what Daniele is going to talk about next.
Thank you. I'm Daniele McKinley, PhD student at the University of Amsterdam and ASTRON. I'm going to talk about the discovery of the extreme environment of the fast radio burst source 121102. As Vishal explained, key ingredient for the discovery was the highest detection, highest frequency detection ever of fast radio burst. This allowed us to study a property of the burst known as polarization. In a polarized wave, the electric field has a preferred direction. As you can see in the plot, there are two examples of polarized waves, one horizontally polarized and one vertically polarized. I'll give you a practical example where you can see polarization in real life. For example, the sunlight, when it's reflected off the surface of the sea, gets horizontally polarized, and in fact, you can remove it using polarized lenses on your sunglasses to remove the glare from the water. Now, when a polarized wave emitted from an astrophysical source crosses a region where a magnetized plasma is present, the direction of polarization gets rotated and the radio wave is twisted. The stronger the magnetic field and the larger will be the rotation. And also, the higher the frequency of the wave, the lower will be the rotation. That's why high frequency observations were essential, because the rotation was so extreme that was completely hidden in previous lower frequency observations. In this slide, I'm going to explain you how we detected such a huge Faraday rotation. This is the name of the effect. This is a plot from the paper where in the top two panels, the measurement of the polarization are represented with colored dots at different frequencies of the radio waves. Different colors represent different bursts, while the sinusoidal black curve is the model that we expect at a certain value of the Faraday rotation. The Faraday rotation is so huge that within our bandwidth, the wave is twisted 50 times. Each twist of the wave is one period of the sinusoid. To give you a feeling of what this means, other FRBs with measured Faraday rotation have values 500 times lower than what we measured. Also, I reported another plot from the paper where I report the distribution of galactic pulsars as a function of the Faraday rotation on the vertical axis and dispersion measure on the horizontal axis. The key result of this plot is to show that the fast radio burst 121102 has a much higher rotation measure, well, Faraday rotation, than the distribution of galactic pulsar. The only other pulsar that has a comparable value of the Faraday rotation is located near Sagittarius A, the supermassive black hole at the center of our galaxy. In the past, values so high of the Faraday rotation has only been detected around supermassive black holes. Therefore, we think that maybe one of the possibilities could be that this has something to do with the high Faraday rotation that we detect. But this is just an hypothesis. However, what we know for sure is that the source is located in an extreme environment with high magnetic fields. Now, Jason will present a summary of the discovery and what has been presented so far, and set the ground for the next work to be done.
Great, thanks. So I'm Jason Hessels. I'm an associate professor at the University of Amsterdam and ASTRON, the Netherlands Institute for Radio Astronomy. You've heard a lot of things. I'm going to try and bring them all together and summarize everything that you've just heard and take a look to the future. So the recent major steps forward that we've made with this repeating fast radio burst source, well, Andrew showed you that the bursts have really this surprising, very, very rich structure in both time and frequency. So when we look at both the time axis and the frequency axis of these bursts, we see these structures, these very pointy structures. Should be careful with this thing. Vishal told you about the detections that we've made at higher frequencies than we've ever been able to achieve before for fast radio burst source, and the fact that we've been able to resolve incredibly short time structures in the bursts, as short as 30 microseconds, and we think probably that there are structures in these bursts that are at even shorter time scales than 30 microseconds. And Daniele showed you that the bursts are coming from an environment of really an extreme magnetized, very hot plasma. And we're adding these results to really a pile of other information about this source. This is a fast radio burst source that we have the most information about. So we have, the maximum number of facts or ingredients that we can put together and try and figure out some kind of self-consistent model. So again, I won't go through the whole laundry list, but we know that this source repeats. We know what kind of galaxy it's in. We know how far away it is. That tells us how much energy each one of the bursts has. And now we know a lot more about its local environment, that it's in this extreme plasma. And we know that the bursts have these strange structures to them. So what kind of models are we considering? Well, in the recent Nature paper that Daniele was just discussing, we've been, I think, quite realistic and a little bit conservative in our possibilities. What we've considered, because of the short durations of the bursts, we've considered some kind of neutron star origin, because in many ways the bursts that we see from this fast radio burst source look like the types of pulses that one will detect from a galactic pulsar. They're just coming from much further away and have to be a lot more powerful. So the short timescales imply some kind of very small emission region, some very small object like a neutron star. So that all sounds very nice and logical, but of course there's some problems. And the biggest problem is, well, this source is 3 billion light years away. It's 1 million times further away than the famous Crab pulsar. How do you get that much energy in these bursts that we can still detect them? And also, if these are bursts coming from a neutron star, well, a neutron star rotates quite rapidly if it's going to have this much energy. Where is the periodicity? Is there some kind of underlying periodicity in these bursts? So far, we haven't been able to find one. So we think that the source producing the burst is quite likely likely a neutron star, but the new results tell us that this neutron star is in a pretty peculiar environment. And one of the options that we consider is that it could be near a massive black hole. This would explain this persistent source of radio bursts, or persistent source of radio emission that Betsey mentioned, because the source of the burst is right on top of quite a bright, persistent source of radio waves. This could explain that persistent radio source, because we could be seeing an accreting massive black hole. That could be that radio emission. It also explains the type of environment, because we have this analogy of this pulsar at our own galactic center that also has a very high Faraday rotation measure, and so that all seems self-consistent, but then it raises questions such as, of all places, why would this source of repeating fast radio bursts be near a massive black hole? Presumably, that would not just be a coincidence. Presumably, it would be an important part of the story, but we don't know why that would matter. Also, you could ask the question, do such massive black holes actually exist in such puny galaxies? And we thought it was quite interesting, actually, in the last press conference. I think it was Karen Masters, is that correct? Yeah, she presented some interesting findings that massive black holes seem to be more common in dwarf galaxies than we had thought before. So that's an interesting aspect of this story that we're thinking about. So that's one of the hypotheses, but if the source is very, very powerful so that we can see it at such a large distance, it's likely that it would be very young, and if it's very young, it's quite possible that it could still be in some kind of cocoon, a supernova remnant, or producing a very energetic nebula. So that also sounds quite logical, and it could explain again this persistent radio source. That could be emission from this very energetic nebula around the source, and it's consistent with the idea that you have a young source. But here we have another problem. There's a downside to this hypothesis. That nebula then would have to be 1,000,000 times brighter than the Crab Nebula, which is a really monstrously bright nebula in our own galaxy. So understanding how it could be so bright introduces a new puzzle. So these are hypotheses that we're considering right now, although I should mention, it could be something completely different. And this is a slide from a recent conference that many of us were at that Tony Pirro made. The joke, of course, is that there are far more theories than there are observed bursts. And one of the things that excites me, at least, is that in the coming weeks, we expect that very creative theorists are going to come up with explanations for our observations that we haven't thought of yet. So you're probably asking yourself, how do we make the next step? How do we make progress on this? Well, the key unknowns, one of the main things we need to do is we need to figure out whether there is an underlying periodicity to the burst. So detecting lots of bursts in a short amount of time, like Vishal showed you, is one way of going about this. Using the polarized properties of the signal is also going to give us a potential new way of trying to find an underlying periodicity. Because once we can figure out if there is a periodicity, and if it is a neutron star spinning at a certain rate, that tells us about how much energy is involved, and that can be very useful. The other thing we need to do is we really need to understand the properties of this persistent radio source better to see whether it is really consistent with being some kind of very, very powerful nebula or maybe an accreting black hole. And we're going to be doing that by, for instance, looking at whether that source is polarized, using, for instance, the VLA to see whether we can detect polarization from that persistent source. So to wrap up, in the near future, are we going to figure out what fast radio bursts are in the next few years or so? I think the prospects are really quite good. And this comes from the fact that a huge investment has gone in at a number of observatories to build new telescopes like CHIME in Canada and ASCAP in Australia, but also to renovate old telescopes like Molonglo in Australia, that's the Utmost system, and the Westerbork telescope in the Netherlands, the Apertief system. These are going to be FRB factories. They're going to be radio telescopes that have enough sensitivity to detect radio bursts, but also an enormous field of view, making it possible to scan the skies and find a lot of fast radio bursts. Because one thing that hasn't been mentioned yet is FRBs are very special, and this is a unique source, but they're really not rare. They're happening all the time. We think there are probably about 10,000 FRBs happening per sky per day, and that means every 10 seconds, somewhere on the sky, there's one of these radio flashes. So if you have a radio telescope that can cover a large fraction of the sky, you're going to find lots of these. And once we start finding lots of these, hopefully in the course of this year and in the coming year, it's a foregone conclusion that we're going to find other repeating sources, that we're going to get other precision localizations, and then we can start seeing, for instance, whether this repeating source is really a complete oddball and something fundamentally different, or whether it's part of a distribution of sources with different properties. So I think that's all that we wanted to tell you right now, and I guess I'll hand the floor back to Rick. Thank you.
Thank you very much, not only for the interesting science, but also for keeping to time. So that means we have lots of time for questions, which is good, because I imagine there's quite a few. Helping me today with the roving mic is my new AAS Media Fellow, Carrie Hensley from Boston University. So you'll get to see more of her in these meetings. And then Inga is going to be watching the webcast. So if you're on the webcast and you have questions, please queue those up. But we're going to start here in the room. So raise your hand, and we'll bring the mic to you. We'll start over here. Identify yourself, tell us who you write for, and we'll go from there.
Hi, Lisa Grossman from Science News. There was a supernova that has been repeating that was announced in November called IPTF14HLS, and the results there suggested that it had gone off and then calmed down and then exploded again. And so I guess this is for Betsey, because you said that was unlikely, but now we've seen one. Could the FRB that is repeating maybe be something like that?
Yeah, so that's a good question. I hadn't heard about that result, but that is very interesting, because we typically think of a supernova as a cataclysmic event that blows the star out and leaves a remnant of some sort. So I guess I would want to know more about to say that, but yeah, if there is, I guess it depends on what we mean by explosion. I think we could still rule out the cataclysmic model in that you'd have to have a limited explosion that keeps your original source in that case, but anything that requires an actual star death or destruction would be ruled out still with the repeating FRB. And I'd be curious to know what's causing this repeating supernova.
Are any of the rest of you aware of that particular supernova?
No, I'm not aware of that source. I would imagine.
Well, that's interesting,
it
because that
sounds
was
like
my
those
question
are-
too, Lisa.
Yeah,
do.
clearly. We've got
is
some
this an
homework to do
advertisement?
after this.
Yeah.
But I would imagine that those are maybe hiccups before the, the final explosion of that
Yeah.
star. And if it's still, sorry?
Yeah, Yeah, you can correct me if I'm wrong, but from what I recall, it was more than a repetition of the supernova, or some injection of power, maybe from some compact object within it.
Oh, okay.
Okay, we're going to come, did you want to add something to that? Let's wait till we get the mic so that the people on the webcast can hear you. And tell us who you are, even though some of us know.
This is Shami Chatterjee. I'm part of this team. One of the issues is that these bursts have been seen to repeat in a few seconds. So they're separated by seconds, whereas this hiccup in the supernova was a long, long time separation.
Okay, yeah, Govert's next, so, great.
Govert Schilling, freelance writer in the Netherlands. I believe there's a couple of dozens of these FRBs known so far, and this is the only repeating one. What can be done and what is being done to check the other ones for possible repetition?
Yeah, they're simply being observed over and over again. Some of the apparently non-repeating sources have been observed for 50 or even 100 hours or so without finding any more bursts, yeah. But, a telescope like CHIME, for instance, which is every day going to scan the entire sky, will just kind of naturally go back to every single source they find every day. So I think it would be very surprising if they don't find any repeating sources, yeah.
And I can add to that a little bit. So many of these sources which has been discovered, the position of those sources are not very well known. The position error is quite large. So if you want to go to a different telescope, which is slightly bigger than the original telescope which has discovered it, it's kind of very hard to sort of pinpoint where you want to look. So there are not many things you can follow up, basically. Or if you want to follow up, you have to go to a lower frequency. So we did follow up some pulsar at 800 megahertz from GBT because they were discovered at higher frequencies from Parkes. So there your position error was sort of in the beam. But that's the best you could do.
Okay, we'll take one in the back here.
Hello, call me Mickey. I have one question, simple question, and I have one observation. Simple question is, how did you measure the distance to that burst? You said 3 million or 3 billion light years, I forgot.
Yeah, so I can answer. So we localized the position of the burst very well, and so we looked at optical images to find that there was a galaxy there, and then we used the Gemini telescope to get a spectrum of that galaxy to get its optical light dispersed, and it has strong narrow emission lines from star formation. And those lines had been shifted due to redshift because it's very far away. And so in fact, we used that to find out how far away it was in redshift space or sort of recessional velocity, and then just used the known expansion of the universe to say how far away it must be. And that actually worked out and matched almost exactly what you might have estimated the distance to be based on that dispersion we saw in the pulse and what we think the medium between the galaxies is like. And that was how we got the 3 billion light years.
All right, just follow up a simple question again. Can you measure the distance between Earth to the North Star using same method or something else?
I'm sorry, can you repeat that? Measure the distance to what?
Distance to the North Star.
To the North Star.
You know, North Star is neighbor to Earth.
Well, the North Star is very close, so we can actually measure its distance more precisely. I don't know if we've done it yet, but we will with Gaia. We'll have a parallax measurement where we actually measure a geometric distance by seeing how that position of the star shifts as the Earth orbits around the sun. So we'll have an even more precise distance for local stars. And so we would find them in a different way.
So my observation is, I am a living entity, right? If I put a sensor here, I hear that noise, and if I put it on my leg, I hear the noise. So what's the difference? It's the same thing up and down.
We'll have to take that one after the briefing. So we'll have a question down here in the front.
Steve Marin, freelance. I want to follow up on your answer a moment ago, Dr. Adams. I was going to ask a different question, and then I got confused because I thought I understood from the presentations that the Faraday rotation was predominantly from the source. But it sounded like, from what you're saying, that there's a significant intergalactic contribution?
Well, that's to the dispersion measure.
Yeah,
So that's to the delay in the pulse. And
Okay, with that related phenomenon. But, so then, do you have a model for the extent of the region in which and how big is it?
Yeah, so, well, the persistent radio source has been observed with long baseline radio interferometry. So we know that that persistent radio source needs to be, I think, less than about 0.7 parsecs in extent, so less than a few light years. It could be much smaller than that. The argument for the rotation measure coming from very local to the source is that we see that the rotation measure actually varies in time quite drastically by about 10% or so, whereas the dispersion measure is varying by less than 1% or so. Yeah. Yeah.
Okay, behind Steve. Wait for the mic, please. Thanks.
Sarah Kaplan from the Washington Post. I was wondering, Jason, you mentioned that sort of the next step is to figure out what exactly is this source, and I'm wondering what would it take to know?
You mean the persistent source?
The persistent source, yeah.
Yeah, well, one of the approaches that we're going to take is using the VLA, the Very Large Array, to see whether that source itself is polarized, whether it produces polarized emission. That could be quite challenging because it's, I mean, we would expect that maybe it's far less polarized, has far lower fractional polarization than these bursts, which are almost 100% polarized, but we're going to try it nonetheless. With even deeper, very long baseline interferometric observations, we can put a stronger constraint on how large that source is, and we're continuing to monitor it to see if it has intrinsic changes in brightness as well.
So just to follow up on that, then what would, like, this idea that maybe it's a neutron star acting weirdly, like what would those things tell you about whether or not that theory is?
Well, we want to establish what the nature of that persistent radio source is. If we conclude that it really does not look like an accreting black hole, then maybe it could be consistent with being a nebula. And that's kind of a parallel thing to figuring out what is producing the burst itself. And those two things are linked. I mean, they're right on top of each other on the sky, so we think that they have some kind of physical relationship between them. So we're kind of working in parallel lines. There's almost half of the team is working on the properties of the bursts themselves to understand what produces the burst. The other half of the team is kind of working on the properties of the associated emission to figure out, you know, what kind of environment and what kind of structures are near it. Yeah.
Hi, Katie Mack, academic. I had a question about the ones observed with the Breakthrough Listen project and how they were all, what you observed was all within the first half hour, and then you said that it made sense that you didn't observe any more for the next 5 hours. Can you just say a little bit more about the physical mechanism for that? Why you expect to see them close together and not across the whole time?
Yeah, I'll try to explain a little bit, but I don't think so it's very well known. There is no current model or theory which could explain why we see so many bursts in such a short time. There are some theories which sort of suggest that if there are some sort of plasma lensing, imagine in a case where you have a source which is always producing a pulses, but now there is a plasma lens which comes between you and the source. That kind of enhances the emission for a very short duration. So you start seeing these pulses for a very short time, and once the condition is not suitable enough, then you don't see the pulses. So here we have seen all these pulses for 30 minutes, but remember, these are the first 30 minutes. So maybe the source was active for even longer than that, and we might just caught it for this last 30 minutes. So we don't really have the exact understanding about how long the source sort of remain in this active state where it produces these bursts. Otherwise, we could really try and understand the size of the plasma lens, and all these things are possible, but that's sort of still something we need to do with the future observations. So there are both ways, but it's very hard to explain if it is something that's to do with the source, where it's easier to explain so something to do with the environment.
Inge, do we have some online? Okay, we'll take a couple of those.
Here's a question from Daniel Fischer from Abenteuer Astronomie in Germany. Still wondering how typical this one repeater is for the whole FRB field. If you look at the individual bursts from the source, do they have any properties not shared by the sources that have been seen bursting only once?
Yeah, it's a very good question. It's one of the, I can start off by, that is one of the fundamental questions, whether in the search for these short duration radio bursts, I'm not sure who I should be looking at because I guess they're not in the room. I'll just look straight ahead.
Yeah.
No,
they are watching you.
Yeah, so one of the fundamental questions is in the search for these short duration radio bursts, we found a number of them. One is repeating, the others haven't been seen to repeat so far. Have we, in the course of these searches, already found two fundamentally different physical processes, two different sources that produce bursts that are quite comparable? They seem to be at similar distances. They have roughly the same durations. These structures that we're seeing in the repeating burst have not really been seen in any other fast radio burst source before, but here we've really zoomed in the resolution. So it's quite possible that other radio bursts will show such features once we're able to take higher quality data on them. And in fact, we know of unpublished results where that is actually the case, that you can zoom in on other fast radio burst sources that apparently don't repeat, but also show a lot of structure in their bursts. And in what other ways can we probe this? Sorry, what was the original question? I've gone on a bit of a tangent here. The original question was?
The original question was how typical this one repeater is for the whole FRB field.
Yeah, so far it seems to be quite atypical. It's doing a lot of stuff we haven't seen in other sources, yeah. One of the things we would like to understand is maybe, the fact that it is atypical in a number of different ways. It has this extremely large Faraday rotation, it's repeating, it shows these strange structures in the burst. Maybe all of those things are actually related to each other, and maybe they are the reason, for instance, why this source looks different than other sources. And to clarify what I mean a little bit, Vishal was just talking about plasma lensing maybe making the bursts brighter than they would otherwise be. That is a possible explanation for why this source is seen to repeat, whereas others are not. And that structure that produces this lensing to make them brighter could also be the same structure that produces this very large rotation measure. So it's possible to come up with a self-consistent explanation for all of this, but it's not necessarily true.
Thank you.
Anything else on that? No? Okay. I actually wanted to make a comment. You're all younger than I am, and I'm not sure if you remember what it was like when gamma ray bursts were first discovered, and there were more models than there were bursts. And we didn't even know the distance for years and years. It took the Compton Gamma Ray Observatory to convince everybody that they were extragalactic. So in some ways, you're ahead of the game because you at least know of one source that's definitely extragalactic. You've got a distance, an environment, all this other stuff. So, but it took a lot of years, to get it sorted out. And now we're still playing with gamma ray bursts in connection, for example, with the kilonova and the gravitational waves. The question is this a particular kind of gamma ray burst, and why is it a little different than the other ones like it, and so on. So it's very interesting to see the history kind of repeating itself.
Yeah, people have told us this before, that, I remember when you went through the same struggle, when we went through the same struggles with understanding gamma ray bursts.
Yeah, there was even a time when the Hubble Space Telescope couldn't focus. I mean, can you believe that? There's people in the room who've always known the Hubble Space Telescope as this, Let's not go there. All right. We're going to come back down to Govert here. Carrie, you should stand in the middle of the room so you don't have to run from one end to the other every time.
One of the models on the list that Jason showed, this is actually a question to Vishal, I guess. One of the models that Jason showed was the light sail theory. You're working for Breakthrough Listen, who's doing SETI research. Do the new observations really exclude the possibility that there's an artificial origin to these bursts? And why does Breakthrough Listen observe these bursts at all?
Yeah, so as far as the FRB 121102 goes, I don't think so there is any slight possibility that they are from any extraterrestrial intelligence, because we already know that this source is located in a dwarf galaxy, which is like a 3 billion light year away. The interest for Breakthrough Listen for FRB, as I said, is that we have this very fascinating instrument, and we always want to push the boundary so that we can explore these phenomena for which we don't understand the origin, for example. So that's one of the reasons why we try and explore FRBs with our instrument. Of course, there is a SETI angle a little bit with that, but as far as I think for this FRB 121102 goes, I don't think so we are really thinking in that direction.
Okay, now we'll go back here. We'll start with Christine, and then we'll go back corner.
Hi, Christine Pulliam from STSCI. Can you briefly explain what a plasma lens is? Is it anything like gravitational lensing?
Very briefly, it's not an area of not an area of expertise for me, but the way I would think of it is just with very simple geometric ray optics of rays being, bent by some plasma structure, which, if you're looking at the source from the right direction, those rays at a certain point, if you're at the right spot, can all come to a point because they're being bent by this lens, let's call it, and then you can have perceive a much brighter source than you otherwise would. And of course, there's going to be places where the rays are actually diverging from your point of view, and the source will be much weaker.
Well, oversimplifying, a huge magnifying glass made of plasma.
But you can think of it in terms of simple ray optics and rays coming back at a certain point.
So it's more acting like an optical lens than a gravitational lens.
Yeah, it's not a gravitational lens.
Yeah. Okay. All right. So we'll go in the back corner.
Hi, this is Pragati Pradhan from Penn State University. I think this question is for Jason. How do you rule out the possibility of this FRB being in a binary system, probably?
Oh, it could very well be in a binary system. So if I did mention very briefly that we haven't been able to find any periodicity to the bursts. So you start to think about ways to explain why we don't see a periodicity yet. One possibility, of course, is that there is no periodicity. Maybe the source is not a rotating object at all. But if it is a rotating object, if it's in a binary system, that's going to make it more difficult to find a periodicity. And another option is if the bursts are very complicated in their structure, and as it's rotating around, if it's constantly producing bursts, if they don't all come from the same spot on the star, then it also makes it much more difficult to find underlying periodicity. So we really cannot rule out that it's in some kind of binary system, and in fact there's a whole class of models that involve binary systems. For instance, a neutron star and a white dwarf that are in a very, very tight orbit, and their magnetic fields are interacting with each other, and reconnections between those magnetic fields are what are causing the radio bursts.
Any other questions here in the room? Any other questions online? Christine, I should apologize since you're from STSCI. I shouldn't have mentioned the Hubble being out of focus. Sorry about that. Yeah, right. I know. I've been disinvited from the press.
Question there.
Question over there. Ah, we got one over here. Okay, great.
Hi, Josh Dillon from Berkeley. I was curious what hope there was to learn more about the host galaxy, in particular, potentially measuring the mass of the supermassive black hole if it exists via the stellar dispersion. Is it too faint for that?
The short answer is it's too faint for that. So we've learned a lot about the host galaxy, but we have no direct evidence for a massive black hole there, and it's too far away and too faint for us to be able to detect it directly. The path forward I see for understanding more about the host galaxy is not studying this specific host galaxy, but hopefully localizing many more FRBs so that we have a class of host galaxies and can study them as a class and maybe get lucky and some are closer and easier to study.
Steve has another question down here.
Yeah.
If I could just follow up on that, I assume that somebody's looked in X-rays and there's no X-rays from the black holes. That
Yes.
avenue is out.
Yeah,
Yes.
there's very deep Chandra and XMM
Yeah.
observations that found nothing at all. Yeah.
Okay, then we have another one?
We have
Thank
another
you.
one.
All right. Carrie's getting quite a
Miguel
workout.
Enriquez from Berkeley. So I was wondering about the periodicity search. What is the shortest periodicity you have searched, and if the actual structure that you see, there could be actually periodic pulses.
The structures in the bursts themselves don't appear to be strictly periodic. If you're asking whether these peaks have a periodicity to them, they don't appear to.
And I mean, I can comment on the periodicity search with Breakthrough Listen because that's the shortest amount of observation where you have largest number of bursts. So then you could do a more precise periodicity search, but we haven't found any good periodicity match.
It's those bright lights that are causing me to miss the hands. Okay, I don't see any more hands, right? All right, I want to remind everybody that, that the news is embargoed until 1 p.m. There have been 4 press releases that I know of that went out under embargo, so if you're on the embargo-eligible press list, you will have received those this morning. Those who are on the rest of the press list will get those plus another 1 at least at 1 o'clock. And I appreciate your cooperation in keeping the lid on it until then. I want to thank the panel again for a very interesting and well-coordinated set of presentations, and I want to thank the folks at Nature for Leslie. Thank you, Leslie Sage, and his team for coordinating with getting this briefing to happen today. So that will be it for this briefing. We have one more briefing today. It's at 2:15 p.m. It actually involves 2 more papers that are appearing in Nature, unrelated topics. And of course, the Nature embargo expires at 1, so you won't have that no tweeting restriction for that briefing. But we hope that if you're planning to write about either of those papers, that you'll stick around for the briefing before you publish anything, because you'll have an opportunity to speak to the authors and do some interviews. All right, so with that, I'll wrap this one up. Thank you all. Thank those of you who are on the webcast, and we'll see you again at 2:15.